Good evening, everyone, and thank you for joining me. So, as this is my second lecture on finite element method and their basic application, and then basics of finite element methods, and for elliptic and parabolic PD. So, as you know that I am Professor JIWARI from Department of Mathematics, Indian Institute of Technology, Roorkee, India. So in this continuation, so yesterday we start the distribution theory. So as I told you that there is a distribution derivative, so which is the generalization of the simple derivative in the bigger space. So now, so what is the distributional derivative? So first, what is the motivation behind this? What is that motivation? So to generalize the concept of differentiation, let f is f belong to C1, or this I am saying here the closed interval. Later I can assume that this is here. This is the motivation behind the distributional derivative. So later I will assume that this is this. So f belong to C1 continuous and differentiable function one time, and phi belong to this one, d of omega. As you know that what is d omega? Yesterday in last lecture we defined this is and sometime we denote this by some another CC infinity functions. So integration by parts it. Now start with this one, a to b f dash phi dx, because f dash f belong to C1, so its derivative is okay, it exists. Then applying here integration by parts, so this is at the point AB, because phi is the function as it is, integration of this phi dash minus a to b and f phi dash dx, and this term becomes 0 because phi belong to d of omega, and this will become phi of a, phi of b become 0 due to the CC infinity functions which have the compact spot. So this term becomes 0. So we have this one, a to b f phi dash dx, or this can written in another way in the duality form. So this is phi dash, and this you can say this is inner product type, and this for all phi belong to d of omega. So here omega is what? Omega is the interval a to b. So this motivates, because this means that we can write this in this form. We are pushing the derivative of f over the function phi. So this becomes, so this motivates to define the to define a derivative of a function of a, you can say, distribution, because here we can consider that f is f does work in some sense of a distribution. So of a distribution, since f can be a distribution here, and this can be written as in this way. So in the right hand side you can see that it is not necessary that because this is equal to this one, if you have to calculate this one, so in place of this you can find this one, but here need not necessary that f is a differentiable function, because this is okay if this term, total term f into phi dash is the piecewise continuous, then we can say that this is the this integral like this, then for this total function should be piecewise continuous. So then this is okay. So if so from this one we can motivate from this integral, and then we can define the distributional derivative if t belong to d dash of this. As you know that d dash is what? Dual of this space. So dual of this space belong to this, and omega is, as we defined, closed interval ab, or you can define this as open interval, because here is just this is the integration. If it is closed interval, if it is open interval, there is no problem. Then define dt as d of t over the function phi. If I am applying this one, so this is equal to, means I am applying like this. So this is equal to minus t of d of phi. So here, if you will compare this and this one, so here this dash is just define the derivative of phi for all phi belong to d of this. Okay, so this is here, define the derivative of phi. So now, so this is the definition of, this is the definition of distributional derivative. So this distributional derivative is linear and continuous both. So we can prove that this is linear, and second thing we can prove this is the continuous. So for the linearity one, just choose two function phi 1 and phi 2 and multiply alpha 1 phi 1 plus alpha 2 phi 2 and prove that this is equal to d alpha 1 d of so for this you have to prove that d of dt of phi 1 alpha 1 phi 1 plus alpha 2 phi 2, that is equal to alpha 1 dt of phi 1 plus alpha 2 dt of phi 2. Then we can say that this operator, because this is some operator over the function phi, so we can say that this is the linear. And for continuity one, so we have to prove that for continuous one, if you have to prove this is continuous, so for this you have to choose a sequence of function phi n which converges in phi in this space, and then you have to prove that dt of phi n converges dt of phi in the same space. So then we can say that this is the continuous one. So for this we have to prove taking a sequence which is converges in this space, then after applying the operator dt, and if you prove that dt of phi n converges to dt phi, then we can say that this is continuous. So so first one is, this is just easy to prove that, just apply this definition here. So this becomes t d alpha 1 phi 1 plus alpha 2 phi 2, and after taking, because this is linear in both, this is bilinear, so you can prove that the first one alpha 1 dt of phi 1 plus alpha 2 dt phi 2, and this is okay. So second one, to prove second one, I will prove the second one. Now start with this one. I have this given, this converges to this, so this means phi of phi n minus phi goes to 0 as n goes to infinity. So now I am starting with this one. Now start with this dt of phi n, that is equal to, by using this definition minus P d of phi n. And as you know that here this phi n converges to phi, so we can say that this converges to minus of T d phi, and this is what? This is nothing, this is the T d T of phi. So this means dt belong to dash of this. So hence we can say that this implies this is d of t is continuous. So more precisely we can say that here, if t is a distribution, more precisely we can write more precisely, if T is a distribution, then T belongs to d dash of this. And if we have to define, because this was the first order derivative, so if you have to define the alphath derivative, then the alphath derivative of this is defined in the sense we can denote this by d alpha of t, and obviously that this also belonging to this dash, and we can define the alphath derivative is defined as, and we denote this by this d alpha of t, and this function, this operator you can say belong also d dash this, and this is defined as d alpha t phi, that is equal to, similar to this one. Now, because what we are doing here, we are pushing this derivative over the phi, so minus 1 power here alpha, and this becomes t and d alpha, and phi, for all phi belong to d of phi. So in this way we can define the alphath derivative. So this is the derivative in distribution sense, as we told you that in last lecture, that it may happen that a function is not differentiable, but its distributional derivative exists. So I can give an example whose classical derivative doesn't exist, but its distributional derivative exists. So let here the domain of our domain is minus 1 to 1, and choose the function fx is equal to mod x in this domain. Then we have to prove that, because you know that the classical derivative of this function doesn't exist, the classical derivative of fx doesn't exist, because at x is equal to 0, so the derivative of this doesn't exist. Okay, doesn't exist at x is equal to 0, but its distributional derivative exists. So how to start this? So again, choose a function phi belong to d of omega. Omega is here, this one, minus 1 to 1. So start with this d of f phi, that is equal to minus of f and d of phi. D is just the first order, you can say first order derivative, because here this was the alphath derivative. Okay, so now So I am starting with this because this was t dt f phi and this was equal to this. So I am saying here this is the derivative of the f and defined by definition this is equal to this, and this can be written as minus integral over the domain f d phi, and for simplicity I am writing here dash phi dash because d phi means this is the first order derivative of phi. So I am simply, for simplicity I am assuming that this is the dash, means simple derivative. Okay, so this is just notation here. This is not the classical derivative. Okay, but obviously that phi belong to this space, and this space has infinite time continuous and differentiable function. So now this can be written as minus f is what? F is this, and you can say this is x and minus x and plus x, minus 1 less than 0 and 0 less than equal to. So this is the value. So I can break like this here. The value of minus 1 to 0 x, this is minus, so this minus plus phi dash and dx, and again this minus here, so 0 to 1 x phi dash and dx. So now integrate by parts in both of the terms. So this can be written as, first function I am saying x is here, integration of this is phi at minus 1 to 0 and minus 1 to 0. So this become phi and dx. So similarly we can this again by parts, first function and integration of second function, and this become plus 0 to 1 phi and dx. So this is equal to, because when you will put 0 here, so this becomes 0, and minus 1 because phi belong to this d omega. So here this become minus 1, and at 1 at boundary the phi becomes 0 because this function contain the CC infinity type functions, have the compact super at the boundary, these are 0. So when you will put minus 1 here and phi of minus 1, so this becomes 0, and according to 0 this is also 0. So we have just minus 1 to 0 phi dx, and when you will put here 1 here, 1 phi of 1 again 0 and 0 again 0, so just we got 1 to this and dx. Okay, if you remember there is a function, Heaviside function, this can be defined minus 1 to 0 and this one. This is the Heaviside step function. So use here means I can say that hx value is minus 1, that is equal to this one, minus 1 here, and hx value is 1 over this interval. So you can write this term as in term of hx and just phi. So you can say this term is equal to integration minus 1 to 1 hx and phi x and dx. When you will open this one, according to this definition of capital H, so this become minus 1 to 0 phi dx and plus 1 phi dx integral over the 0 to 1. Okay, so this means what? So what we got? So we got this implied, we start this df phi and that is equal to h and phi, this one, because this can be written as this. This is the inner product type. So h and phi dx. So when you will compare, so this implies d of f is equal to h. If you will compare from this and this, So the derivative, first derivative of this fx is nothing, the hx function, that is the Heaviside step function. So, but as I told you that the classical derivative of this doesn't exist, so we can say that the distributional sense of the derivative is more general form of the derivative. So again, if you want to find again one more derivative of this function is now hx. So this function, again you can say that this is not the differentiable here, because this is not continuous here at x is equal to 0. So but we can find its again distributional derivative. So to find, if you want to find, the distributional derivative of h, start again the same thing, start with this dh and phi, this one, and apply the definition of the distributional derivative, that is equal to minus of hx and phi dash, or you can say in place of phi if you want to say here d, then this become phi dash, that's the problem. So this is equal to this become minus of integral minus 1 to 1, again the same domain and the same hx phi dash and dx, and this can written again because its value minus 1 and 1, so this become phi dash minus 1 to 1 dx and minus 1 to 0 and 0 to 1 phi dash and dx. Apply here, because this is phi dash, its integration is phi, put the limit, again the same thing, so and use this one, phi of minus 1 is equal to 0, phi of 1 is equal to 0. So finally what we got this one, phi of 0 from here and phi of 0 from here, and that is equal to 2 of phi of 0. So from here its value is this one, so we cannot say that what is the derivative of this. So to find the derivative of capital H, so we have to write this in this form, means something should be there, some function here and phi should be here, then we can say that that function is the derivative of this capital H. So we know there is a property of Dirac delta function that is called shifting property. We know the integral minus 2 plus x minus a f of x dx, this is equal to, this is the Dirac delta function here, its center at a, so its value become phi of a here. If its center is just 0, so its value, this is the property, so from here we can write also minus 2 plus Dirac delta function just center at 0 fx dx, that is equal to phi of 0 here. So means that I can apply here this Dirac delta function, but domain is minus 2 plus infinity, that's no problem. I can say this is minus 1 to 0, minus 1 to 1, because this is the, because due to phi, this becomes CC infinity function, and that is equal to 0 over here. So means that this I can define, this term can be written as twice time outside and Dirac delta function here and phi here. When you will define this, this is equal to what? This is twice time and minus 1 to 1 Dirac delta here, phi and dx, this one. And apply this one. So when you will apply here this one, because this is from minus to plus, but this is also the same, there is no problem. So when you will apply here, so this value is phi of 0, so that is equal to phi of 0 and 2 is same. So if you will compare this and this, so you can say that the derivative of Heaviside function is nothing twice time of the Dirac delta function. So this implies, so we got dh phi equal to twice time Dirac delta function, and this for all phi belong to d of omega. So this means d of h is equal to 2 of delta. So see here, this function was not continuous. Obviously, it is not differentiable in classical sense, but its distributional derivative exists, and that is equal to 2 times of the Dirac delta function. So this was distribution theory. So after that, there is also come the weak derivative. So weak derivative is also a special some special case of this distributional derivative. So I can define what is weak derivative here. Weak derivative, as I told you, that this is the special case of distributional derivative. Okay, so for this, because this is special case, here there is no condition of the phi f, but here what is the condition? That u and v belong to L1 space and locally here over some domain, means that u and v both are integrable function, but locally, not the globally. It is the locally, and yesterday we defined what is the local space, L1 space. So, and alpha is multi-index parameter, as we defined in last lecture. Alpha is nothing just alpha 1, alpha 2 and alpha n. We say that, then we say that v is the weak derivative of u if the integral should exist, means integral over this domain u d alpha phi dx, and that is equal to -1 our mod alpha here, and integral over v and phi dx for all phi belong to C0 infinity function, and v is the alphath weak derivative, means alpha is the multi-index, and obviously that you know that mod of alpha is equal to what? Alpha 1 plus up to alpha n. So, and we denote this by d alpha of u is equal to v. This means the alphath weak derivative of u is equal to v if this integral satisfies. Means that if suppose you have to find the first order weak derivative, so alpha will be 1. So u phi dash is equal to -1 here, alpha is 1 here, so v phi. Then you compare that this v is the weak derivative of this u. So similarly, as to distributional derivative, we can give the example of weak derivative. Similar to distributional derivative, we can give the example of weak derivative. Again, the simple example, this one. Let I'm choosing n is 1, means one dimensional case, and domain is 0 to 2. Define a function ux that is this one. Ux is equal to x between 0 and 1, and between 1 and 2 its value is 1. So there is no problem, this is continuous function at x is equal to 1, this is 1. So you can write it 1, there is no problem here also. And define one more function Vx, just differentiate simple way. I am not thinking about this is continuous or not. So just derivative of x is equal to 1 and derivative of 1 is equal to 0. So I have defined another function Vx. So I will prove that here the Vx is the weak derivative of this Ux. So for this, because I am talking about the first order weak derivative, so from here you have to prove that u phi dash is equal to -1 v and phi. Then we can say that the v is the weak derivative of u. So here required to prove what you have to prove. We have to prove that u dash is equal to v, or you can say d u is equal to v. Some sense this is thus d denote here the weak derivative, and this is also weak derivative, not the classical derivative. So start from the left hand side of the definition. Integral over the domain 0 to 2 and u here and phi dash and dx, that is equal to. I am starting from the left hand side, and I will arrive here and then compare that. This is the weak derivative of this. So start from here. The value of u is x over this interval and 1 over this interval. So this become 0 to 1 x phi dash dx plus 1 to 2 and phi dash and dx. Okay, so now see here, you can integrate this by parts. This is okay, this is phi dash, so its integration is phi, and you can put the limit. But here integration by parts, so first is okay, integration of this function 0 to 1 minus 0 to 1 and phi and dx. So plus phi of 2 minus phi of 1. Integration of this, and after putting the limit. When you will put this limit, this will give phi of 1 minus, because at 0 this is 0, and phi dx, and plus phi of 2 minus phi of 1. This is phi of 1 is cancelled out. And at phi of 2 is 0, because 0 and 2 are the boundary of our domain, and phi is what? Phi is from this, or you can say CC infinity as C0 infinity function. So this is also 0. So finally just we got here -1 0 to 1 phi and dx. So I can write this in with respect to v also, because v value I can say plus, suppose I am saying here plus, this is minus here, okay. I can say plus or minus 1 to 2, 0 and phi dx. I can write this as. There is no problem because this is 0. So 0 phi dx. So now you can see from here, here is 1. So this is v 0 to 1. At 0 to 1 its value is 1, and 1 to 2 its value is 0. So you can say this is equal to minus 0 to 2 Vx, phi x and dx. Means when you will put the value of v here, so you will get this term and this term. Now compare this and this. So from these two integrals, so you can say that this implies d of u is equal to v. So v is the first order weak derivative of u. So there are many functions whose classical derivative doesn't exist, but weak derivative exists. So generally in finite element method we use the weak derivative. Means anywhere if you are saying d alpha u or d alpha v, so this means these are the weak derivative in distribution sense, because as I told you that the weak derivative is the particular case of the distributional derivative. So this was some more definition I want to just explain here. What is the functional? Yeah, functional is also important, because when you will apply the finite element method, so we will make the weak formulation, and in that one we define the functional. So what is functional also here? Let V be a functional space, function space, or you can say vector space. So f is any function from V to R is called functional. It's called functional, and it is defined as f of v is equal to capital F and V. This is the, you can say, duality in some sense of the inner product. So this is called functional. So there are two properties of this functional. First thing is that this is linear. Second one, this is continuous. If you have to prove this is continuous, for linear one, you have to prove that the same thing, alpha u plus beta v, that is equal to alpha f of u plus beta f of v. And this is just very easy, because this side is the inner product, so you can define, or you can define this in integral form, integration f v dx. So alpha and beta are the constant, they can come out, and this is summation also we can make separate, and then finally we can say this is equal to this. So it is easy to prove. I am leaving this on you. So now to prove the second thing, continuous one, if you prove that this functional is bounded, then that is enough. Means to prove continuous, of f, it is okay to prove f is bounded. So for boundedness, what you have to prove? So this is bounded. F is bounded if there exists some constant greater than 0, such that mod of f of v is bounded by C and norm of v over the space V. For all, this is for all v belong to capital V. So if this happens, so then we can say that this is bounded. So to prove this is continuous, so to prove it is bounded, then this is enough. So we can define here V dash, that is what? Dual of V, this space what? Those functional means the function which are from V to R, f is linear and continuous. Means V dash contain those functional which are linear and continuous. So that space is denoted by dual of capital V, and it is denoted by V dash, and this become norm space. This become norm space with norm. Norm is defined like this. Okay, no, because this contains functional. So norm of this defined as supremum of mod f of v, norm of this here, and supremum of this here, but this contain v belong to capital V, and this means that this all the element which are non-zero here, because in denominator there should be no zero, so that's why it is written V minus. This is just notation, V minus, capital V minus 0, means 0 element is don't have this. Okay, so now, so from here and from this one I can say this is a star, this is a star, and this is double star. Suppose I am saying this is double star. So I can prove from here, because what? Its value is bounded by C and this. So if I am applying here, this mode of this is bounded by C and this. So so this is cancelled out with this one. So you can say from star and double star, we have norm of capital F over V is bounded by C. So we are also thankful some inequality here, because we use some inequality also, some important inequality. Some important inequality is here. So first one is Poincare inequality. What is this? Let this be a bounded domain of Rn. There exists constant, and obviously that this constant depend upon the domain. So such that, so this means norm of u over L2 here. L2 is bounded by C omega. You can write V H1. This is the seminorm, you can say seminorm, and or sometime you can write this as L2 less than equal to C omega del of this L2. Obviously L2 of omega, L2 of omega. Okay, so we can define this as. So there is one more inequality, Grunwald inequality. Grunwald inequality. Let A belong to L1, T naught to capital T. This is interval here. A belong to L1 integrable function over this interval. Be a non-negative function and G and phi are two functions, continuous function over the interval. This if phi is such that phi of t less than equal to g of t plus t naught to capital T, a of ta, phi of ta, and d ta. If this for all t belong to this interval, then then what will happen? Then we can write this as then phi of t is less than equal to g of t, means this g of t and exponential of t naught to capital T and a of ta and d of ta. So this will be happen for all t. For all t belong to this. So we can prove this if we have these things, then we can write phi of t less than equal to gt. This gt was in plus, so here in multiplication gt exponential of this. So we will use this one also. So third problem, you can say there is a Young's inequality. Young's inequality is what? This says for a and b greater than equal to 0, p and q greater than 1, then for two real numbers ab less than equal to ap by p plus bq by q. A and b are some non-negative real numbers. A and b are some non-negative real numbers, and p and q some exponent which are greater than 1. So then we can write ab is bounded by ap divided by p plus bq divided by q. So there is one more property here. This the Cauchy-Schwarz inequality. Cauchy inequality. This is what this says. U and V, the inner product of this is bounded by norm over L2. Norm over L2. So we will use this inequality in further to develop the finite element theory for the elliptic PDEs and then for the parabolic PDEs. So now the most important thing for the finite element method is the Sobolev spaces. So till now we have explained, we have give some brief idea about the basics of functional analysis elements, the elements of functional which are used for the finite element theory. So now there are the Sobolev spaces. These are very important because we will develop the theory of finite element method in Sobolev spaces. Okay, so before that you should know what is the Sobolev space and what are the properties of Sobolev spaces. So Sobolev spaces are defined by Sobolev are defined as WMP over some domain omega that is equal to V belong to LP space and their alpha derivative, obviously these are the weak derivative, also belong to LP space for all mod of alpha less than equal to. Means that if this m is some two numbers, suppose I am saying m is equal to 2, so means that this space contains those functions which are from LP space and their weak derivative up to alpha order. Alpha is what? Mod of alpha less than equal to m, also from the LP space, and these spaces are block spaces with norm. These are block spaces with norm. If you define the norm MP, norm of U, MP means that's WMP if you write here. So you can write WMP is equal to summation mod alpha less than equal to M and integral over the domain omega and d alpha of u power p dx and power 1 by p. So this for all p less than infinity. This is for all p less than equal to infinity, but less than infinity, sorry, not equal. So for p equal to infinity, we can define another norm, that is, you can say L infinity norm. So for u m infinity, this is nothing, this is the just maximum over mod alpha less than equal to m, and norm of d alpha u over L infinity, this one for this is the for p equal to infinity. Okay, alpha, already you know that alpha is the multi-index, alpha 1, alpha 2, alpha n, and so on. So these are the Banach spaces. These are called Banach spaces. Obviously, these spaces are also the Sobolev spaces. So these are Sobolev spaces which are Banach spaces under this norm and this norm. So this is easy to prove. I am not going to prove these are Banach spaces with the help of this norm and this norm. Now, actually we are not interested because m is here, p is here from this and this. So we are interested only just for p equal to p. For p equal to 2, these spaces become Wm2, or that is denoted by Hm space. Okay, so we are particularly interested Hm spaces. Okay, Hm spaces are what? Here p is equal to 2, so this means v belong to L2 and their alpha derivative is also belong to L2, and condition over alpha the same, this one. Okay, so we will use these spaces for the finite element theory. For example, suppose I am saying that for example I am saying m is equal to 1. What is m? This type of space Hm. Mostly we use just H1 space, H2 space, maximum up to H2, because if you will go H3, H4 and higher, so there we require the higher regularity for the solution. So H1 space, these are defined, V belong to L2 such that the alpha is just alpha belong to also L2, but here alpha is just less than equal to 1, means that it can be just maximum 1. So we all already belong to this. This means when you will take alpha is equal to 0, so d0 u, oh sorry, here also d0 v also belong to L2, means this v belong to L2, and when alpha is equal to 1, so d alpha belong to L2, means first order weak derivative is also in L2. Okay, so and one more thing generally we will use here. So H01 space, H01 space means the function which are in H1 such that v is equal to 0 on the boundary of the domain. So this is H01 space which are 0 over the boundary and all function from the H1 space from the above space. Okay, so now, okay, one more thing you can define if you want to, H2 space for m is equal to 2. This means v belong to L2 such that the alpha of v also belong to L2 such that mod of alpha less than equal to 2. So one more important is here H02. So here v belong to H2 such that v is equal to 0 and del u is also 0 on the boundary of this. Means this and this value is also 0. So in this sense, later we can prove that this this del, you can write here the directional derivative. Directional derivatives are in the this into some vector, so directional vector. So this made that is equal to 0. So directional derivative also 0. So if your boundary condition are Newman type, so in that case we apply this one. So these are H1 and H2 space and HK space. So these are Hilbert space, not Riemann, but for p equal to 2, you know already that for p equal to 2, the LP spaces are Hilbert spaces only for p equal to 2. So for p equal to, that's why we are interested only for p equal to 2 Sobolev spaces, because that are the Hilbert space, and with the help of this we can easily apply the property of Hilbert space for the elliptic theory of the elliptic problem and for the theory of finite element matter. So H1 is HM are Hilbert space. Hilbert spaces with obviously that Hilbert space means if it is inner product space and it is complete. So for this, if it is, we define the inner product in this way: summation less than equal to m and integral over the domain d alpha u, d alpha v and dx. So this is the inner product here, and norm can be induced from here also, because here just p is equal to 2 here. So p equal to 2 means this power 2 and 1 by 2 and this. So norm can be taken from the definition of Sobolev spaces. So these are the, so I can define this norm also so that I can visualize something. So Hm, that is equal to summation mod alpha less than equal to m here, and norm of d alpha u square, and here also square if you want to. Otherwise you can take 1 by 2 both sides. Okay, here you can say the solution is over m this. So when you will define, when you are choosing H1 space, so for H1 space the norm will be like this: norm of u over 1. Sometimes it is written like this, or people write u1, m here. This means HM norm. This is the HM norm. So I am writing here 1. This means H1 norm. Or sometimes you can write H1 also. Both are same thing. So this, or that is equal to, here m is equal to 1. So when you will open the summation, so this is norm of alpha is equal to 0 here. So alpha 0 means just u square plus this d of u square. First derivative you can write just norm of this square plus norm of del of u square. So H1 norm, okay, this is square. H1 norm is defined by norm of this is over L2, this is over L2. Okay, so similarly we can write the norm for H2. So just one more term will here in H2, that is equal to this square. This is for the H2 one. Up to here H1, if you will add one more term, so that is goes to H2 norm. So from here we can prove one thing, because that is important here. Because the H1 norm is what? H1 norm is this one. This is H1 norm. But here there is a one theorem. H1 norm defined by, you can say its name, you can say suppose I'm saying star, defined by star and one more norm is and the norm del u, this is just del u are equivalent. Are equivalent. So this is very important because generally we use this theory that this norm and h1 norm means this is just norm of u h1. So these two norms are equivalent. So we know by definition, if you want to prove is just very easy. You know that two norms, I am saying that any two norms are equivalent if I am saying the norm, I am also saying the norm. I am saying this is one norm and this is another norm, just giving some name. This is here is 3 and 3 here, 3 standing line, 3 standing line, 2 standing, 2 standing. So these norms are equivalent if when these will be equivalent. So for this there is a constant C1 and C2 such that C1 less than equal to this less than equal to V less than equal to C2 and this like this. For all V belong to some norm space V. So this is the definition of two equivalent norm. This is one norm, this is two norms, so there exists some constant C1 and C2 such that we satisfy this one. C1 norm this and norm and this. So these are called the equivalent norm. So we have to prove here this norm and this norm. Means this norm and this norm are equivalent. So this is just from the definition. So I am proving here. We know from the H1 norm of u over 1. I am saying 1. That is equal to what? That is equal to norm of u square over L2 plus norm of del u square L2. If I am not writing here just without L2, this means if I am not writing anything here, means just a norm square, this means these are the L2 norms. Okay, for simplicity I am saying that here L2 norm that is equal to, I am saying like this. So I will use this in whole lecture. If it is nothing here, so this means these are the L2 norm. So from here you can see that what you have to prove, you have to prove that this norm and this norm are equivalent. Means that you have to write this type of inequality. C1 and C2. C1, C2 may be some constant. So from here you can say that if you remove, this is a positive term. So if you remove this one, so you can say this imply less than equal, greater than equal to norm of del square. Say this is just star. So we got one inequality. I will prove one more. So and combine both of them, I can say this is okay. So now again start from this one, this, and that is equal to norm of u square plus del of u whole square. So now apply here the Poincare inequality. Poincare inequality is what? Poincare inequality is this is L2 norm bounded by some constant depend upon omega and this over L2. So this is the Poincare inequality. Poincare inequality. So apply here for u. So this will be less than equal to, due to this less than equal to C omega norm of del u square. Obviously this is L2 here, so L2 here and plus this square. So take this common. So this is equal to 1 plus c omega and del u whole square. Say this is some constant c and del u square. So means that this is double star. When you will combine star and double star, so you can find that because this greater than this, then this greater than is equal to this. So from star and double star, what we got? We got del u square less than equal to norm of 1 square and less than equal to c and del u square. So these are the equivalent now. Okay, so now I think it's enough the basic thing. If something will use in later, so we can define if we require something else, so we can define later. So one more thing, just I am telling you, the dual of H1 space. Dual of H1 space is H01 space is denoted by H minus 1. Okay, so we will denote always the dual of H01 space H minus 1, and this become norm space under this norm minus 1, that is equal to supremum over V belong to H01 and mod of FV and divided by norm of V over 1 over H1. So this is the dual, because sometimes we use H minus 1. So H minus 1 is nothing. This is the dual of H01. So just quickly I am giving one regularity theory. There is a theorem which gives some regularity about the Sobolev spaces. So its name is regularities HK spaces. For this is a theorem. Its name is Sobolev embedding theorem. Sobolev embedding theorem. This theorem says if this is an open set of Rn space, n is greater than equal to 1, provided with a sufficient regular boundary, sufficient regular boundary of this omega, then HK spaces contain Cm. Okay, you can write without brackets. So bar if K is greater than M plus N by 2, means that HK spaces are contained in Cm spaces. Cm means continuous and differentiable up to mth order and uniformly continuous, because bar is here. We defined in last lecture these spaces are the this space means these are the continuous and differentiable function, but continuity of uniform type. So for example, if I am saying K is equal to 1 here, Kevin, what are the element of H1 space? n is also 1, n is means dimension, this is dimension. So if I am saying this one, and you have to apply this condition also, H1 space contain Cm for what, m or not. So this condition should be implemented because k is here, k is 1, so k is 1 greater than, dimension is also 1, so something m here plus 1 by 2. So means that what value of m will be here when this hold and this will satisfy. So if you will take m is equal to 0 here, so this is okay, so this is okay, 1 greater than 1 by 2, this means H1 space containing CG. But when you will go in 2 dimension, it is not necessary that when n is equal to 2, 2 is 1, 1 cannot be greater than this, means that H2 spaces cannot be continuous. Okay, this is for just H1 spaces is continuous in the n is equal to 1 in 1 dimension. Okay, so its lecture is going on here. Okay. Only this? So now start with the finite element method for one-dimensional problem, and that is called finite element method for one-dimensional PDE. So we are starting with elliptic theory. So let's consider our problem minus u double dash is equal to fx. X belong to some domain, this omega, and this omega may be something, for simplicity I am saying this is 0 to 1, or you can take any a to b, that's no problem. So u is equal to 0 on the boundary of this. So this is our original problem. So how to start? Because this is one-dimensional partial differential equation, or you can say this is just ODE minus u double dash f is equal to fx, and over this, and u is equal to 0 on the boundary, or in another way you can say minus u double dash is equal to fx, and u of 0 is equal to u of 1 is equal to 0. Because I have here just consider the domain 0 to 1. So this is one is the strong form. Why it is called strong form here? You can see that here u is what? U is u from C2 space. Means u is twice time continuous and differentiable function. So the original PDE, our original PDE is called the strong form. Now what happens that for the solution of this PDE, it is not necessary that our function is from C2 always, because in some physical problems solution of this problem exists, but that is not a differentiable function up to twice time. So that's why we apply the finite element method and make the weak form, because this is strong form. In weak form we reduce the regularity of the solution. Here u belong C2, if you will see originally, so this C2 over the domain and intersection C1 over the boundary, if f is continuous, means this f is continuous, in that case you will belong to this one. C2 intersection over the boundary, it should be continuous and differentiable due to continuity of this f. Okay, so now what is the weak form now? The first step in the finite element method is weak formulation. Okay, so we have to choose some test function. So that is sufficient regular, and multiply this equation and integrate over the domain. So multiply 1 by u belong to, I am choosing here, thus this v belong to d omega. Omega is, if you want to say 0 to 1, so means v is sufficiently smooth function. Okay, so multiply and integrate over this. So what we got? We got integration 0 to 1 u double dash v dx and equal to f v and dx. Okay, so now just this is okay because we can do nothing here, because this is already, there is no derivative exists here for all v belong to this. So now, yeah, how to?
I need to get my stuff on the table.
This one?
All of them. So can it come or can you just stop?
Okay, just a minute. This also?
Yes, everything. I can bring them, but I just don't want.
Okay, just means I am posing this one. Okay. So okay, you can come and take.
It's already.
Okay, I'm just taking 2 minutes break. I think this is mine. Okay.
And the charger.
Fine.
The charger.
What?
The charger. On the other side. Thank you. Sorry, thank you.
Okay, so now, so we will integrate just the left hand side. Okay, so when you will integrate this, so first function I am saying this is first function, here integration of this second function, so minus is also there, 0 to 1 and 0 to 1 u dash v dash dx equal to 0 to 1 f of v and dx. Okay, now because this is becomes 0, I am choosing here because our solution u is equal to 0 and u of 0 and u of 1 is equal to 0. At boundary initially it is 0. So I am choosing v in such a way that choose v in such a way that v is equal to 0 on the boundary. So this becomes 0. So we have what? So this implies 0 to 1 u dash v dash dx equal to 0 to 1 f of v dx. So now, so say this is 2. So now up to here, just we have we have V such that V is equal to 0 over the boundary. Our motive is what? Our motive is to find a space where we need the very less regularity, and this should be satisfied. So for that, if I am saying, if I am choosing U dash and V dash from the U dash and V dash from C1 space, continuous function and differentiable function, then their product will become to C1, and that is okay. And but sometime what happens that I told you that the solution U is not necessary also differentiable also. Means continuity may be maintained, but sometimes not differentiable also. So if you will choose U dash V dash from C1 space, that is also, and that is also a more regularity. So to reduce this regularity, we can assume because our motive is what? Our motive is this should exist. Exist means this integral should finite, this integral should finite, and that is okay. So this integral when will finite if this is just this function U dash into V dash, this is integrable function from the L1 space, and f into V is also from L1 space, then this is okay. Okay, so we have a theorem that is called Holder's, you can say, inequality. What this says, if U and V belong to L2 space, then U into V belong to L1 space. So this is okay, means that if we have two functions U and V from L2, then their product from L1. So means that if we will choose a space where U dash and V dash belong to L2 space, then their product will become L1. So L1 means this integral will be satisfied. So keeping in this mind, we have only one space. So we have that space. We have that space. What is that space? Because H1 is that space, some domain in which functions are L2 and their first derivative is also belong to L2. Okay. So, but one more condition we have imposed on V in such a way that V is equal to 0. So, if I am choosing one more condition here that V is equal to 0, so that space is what? H0, 1, space V belong to L2 and V dash also belong to L2 and V is equal to 0 on the boundary. Means that for the existence of 2, the minimum regularity is just if our U dash and V dash from L2, then this integral 2 will really exist. So we will, now our problem is what? Now our problem is now to find U belong to H01 such that integral 0 to 1 U dash V dash dx is equal to, here omega is 0 to 1, such that 0 to 1 f of V dx for all V belong to H0. So finally our problem was this 3. So I am saying this is 3. And initially it was first problem. So I can say that what this is the weak form. This is the weak form of equation 1. Means that if this is the strong form by using FEM theory, so this is our the weak formulation of this equation. So now we can, because this is the infinite dimensional space. Okay, so we cannot find the solution of this equation free in infinite dimensional space. So we have to move to finite dimensional subspace of this infinite dimensional subspace, and that is denoted by some space. So if I am saying here, just let capital V is equal to h01. So now for the solution of equation number 1 or this equation, so I will choose a finite dimensional subspace of V, say VH. Okay, and a space VH0, means this is space, just a subspace of this, but I am saying that a space VH0 means those functions belong to VH such that V is equal to 0 on the boundary. That is also a requirement for us. Okay, so obviously that VH0 contain in VH and this contain in this. So means that if you will choose any element from here, so that element will go in this one. Okay, this because this capital V has also the element at boundary which are 0 at the boundary. So now so our here, or you can say, because our boundary is what? Our boundary is 0 to, our domain is 0 to 1, so you can say that V of 0 is equal to 0, V of 1 is equal to, V of 1 is also this. So means that VH is the space which contain the element piecewise linear and 0 at the boundary. So now our problem, because our motive was to define our problem over the finite dimensional subspace. So now this was in finite dimensional subspace. So now come to the finite dimensional subspace here. So now our problem is, find UH, I am saying just UH belong to VH0 such that, because this is just notation here, I said find U belong to H01 because this was in finite dimensional. So here this is finite dimensional subspace. So I am saying VH such that integral 0 to 1 UH dash V dash dx is equal to 0 to 1 f of V dx is equal for all V belong to VH0. So say this is 4. This 4 is called Galerkin approximation. Galerkin's approximation. So, and Galerkin method also, because what we are taking here just the multiply by something and finally this weak form over the finite dimensions of space is called the Galerkin methods. So because this is finite dimensional subspace, obviously that its dimension is something, so I am saying that its dimension is n plus 1. So these are, you can say n. So you can choose the basis of this, because since VH0 is finite dimensional, then let dimension of VH0 is equal to, I'm saying, n, and define its basis, and phi 1, phi 2, phi n are the basis of VH. Okay, so these are the bases. So this means this 4 will be hold for all bases. So this means 4 will hold for all phi i's. That is integral 0 to 1 us dash phi I dx is equal to integral 0 to 1 f of phi I and dx. Say this is and you can keep this I is equal to 1 to n. This hold for all bases. So here I can choose the bases also, because bases are I can choose some functions. So I am choosing here the hat functions. Phi i's are defined by x minus xi minus 1 divided by xi minus 1 over the domain over the interval xi, and this is xi plus 1 minus x divided by xi plus 1 minus xi. These are the, or you can say this is x belong to I plus 1. So what are these functions? This is xi minus 1, this is xi, and this is xi plus 1. So phi is, okay, phi you can say, phi is defined in this phi I. Suppose this is, I am saying I, this is capital I plus 1. This is just subinterval, means divide the domain. Suppose this is our domain 0 to 1. In those finite sub intervals, suppose this is I is equal to I1, this is I2, and so on. Okay, so this is I, capital I plus 1, and so on. So these are the head functions, and 0 otherwise. So you can see that these functions are non-zero over this interval except 0. Similarly, you can define the phi I minus 1 like this. Okay, and this is phi I minus 1. Similarly, you can define phi I plus 1. So these are the head functions, and obviously these are piecewise and continuous one. So there is no problem, and it is all. So phi, you can say that phi 5. This is we have this one, and for all V belong to VH. So our solution is also from this space VH0. So obviously this can be written in the linear combination of this one. Here UH belong to capital VH0, then UH can be written in the linear combination of, suppose J is equal to 1 to N, some constant alpha I and alpha J and phi J. Because UH from the capital VH and VH0 has a basis phi 1, phi 2, phi n. So this can be written in the linear combination of this one. So say this is 6. Now put this 6 in 5. What we got? So we got the system of linear equation and we can solve for the alphas. Here, one thing I want to mention, these alphas are unknown. These alphas are unknown here. Okay, so now put 6 in 5. We get, so summation j is equal to 1 to n, because we have to put this here, just its derivative of phi dash, and this is okay, sorry, so this is also phi dash, because this is v dash, so this is also phi dash. So integral 0 to 1 phi j dash alpha j and phi I dash dx, that is equal to summation I equal to 1 to n integral 0 to 1 f phi I and dx. So here this can be written in this form. Let Aij is equal to 0 to 1 phi I dash phi j dash dx, this one, and bi is equal to integral 0 to 1. Okay, I think there is no integral because just u was in this one. Bi is equal to f of phi I and dx. So this can be written as A, because I am saying this is the Aij, so this total, because this is Aij and this is the Bi, so finally this can be written as summation j is equal to 1 to n Aij, and suppose this alpha j and equal to the Bi, or you can say, or this is A, I am saying this is matrix A, and alpha or is equal to B type, which is linear system, because our problem was linear, so it is linear system. If our problem is non-linear, so this become non-linear, and then you can use some linearization for solving this system. So now here, so solve from here, solve for alpha. Alpha is what? Alpha is alpha 1, alpha 2, alpha 1, this vector, and after computing these alphas, put here, so you can find the solution of our problem. And you can see, for convergence point of view, I will prove after some time the convergence of finite element methods, priori and posteriori both. So when you will increase the n, so this solution will converge to our exact solution with some rate of convergence. Okay, so now come to the, I am leaving here because if you want to go in MATLAB or another software, so Aij we have this one, compute this, or you can use some quadrature rule here to compute this, and finally you will get this system, and solve this system by using any numerical method, and from here you will get the alpha. When you will get alpha, put the value of alpha here, so you will get the solution of the problem. So obviously that what we have done, it was just approximation. So in approximation, always there will be some errors. So what type of error occur here? In finite element methods, we discuss two types of the error: a priori error estimate, and second thing is posteriori error estimate. So in priori or posteriori means that if the error bound is bounded by the exact solution. Means that error means suppose u is the exact solution, UH is your approximate solution, is bounded by some depend upon the exact solution u. So then we can say this is the priori estimate. And in posterior one, we prove that the error upper bound is depend upon the our approximate solution, where u is the exact solution of the equation and UH is the approximate solution. So if your error bound is depend upon the exact solution, that is called the a priori error estimate. If your solution is depend upon the approximate solution UH, then it is called the posterior error estimate. So first we prove the theorem Galerkin orthogonality. Galerkin orthogonality. What is this? Let UH is finite element solution, or we can say approximation, and U is the exact solution. Then the integral 0 to 1 u minus UH dash v dash dx is equal to 0 for all v belong to h. So UH is means UH is the solution of the equation number 4, I think so. 4, yeah. 4. So and U is the solution of the equation number, I think it was 3 equation number, solution of that one. And then you have to prove that U minus UH dash V dash is equal to 0 for all V belong to this one. So proof is just 2-line proof. Given UH is the finite element solution, so UH is finite, I am writing just in short form, finite element solution. Then 0 to 1 UH dash V dash dx is equal to 0 to 1 f of V dx for all V belong to capital V, or that is equal to H0. Okay, so now U is the exact solution of the weak form. Exact, yeah, you can say weak solution. You can say weak solution. You can say weak solution. Then, so 0 to 1. Here you can say is the weak solution. You can say weak solution. U dash V dash dx is equal to 0 to 1 f of V and dx. So here this is wrong. This will be VH0. Yeah, because this is the this is the finite element solution. For all V belong to V, and that is equal to H0. Okay, so now subtract both of them. So you will get the Galerkin orthogonality. Just subtract, say this is a star and this is double star. Subtract both of them. So you can see that subtract star from double star. So this minus this, you will get U minus UH, because V dash is common. So U minus U dash V dash, and this both are same because this content from here and this is the subset of capital V. So subtracting star and double star, we get 0 to 1 u minus u dash uh dash and v dash dx is equal to 0 for all v belong to vh. So actually this Galerkin orthogonality we will use for the further error estimate. So first we have proved the Galerkin orthogonality, and we will apply this for the a priori estimate. And you can say that this means what? This is the, you can say error u minus u is the original solution of the weak form, and this. So finite element solution UH is the finite element solution, and this is the U is the solution of weak formulation or variational formulation. So the second theorem says the error estimate. What is the error estimate for this? The finite element solution UH define here, you can say define in star, defined by, you can say defined by 0 to 1 UH dash VH dash dx is equal to f of v dx for all v belong to VH0. Defined by this satisfies. What this satisfies? This satisfies norm of u minus UH dash, norm of this less than equal to u minus v dash for all v belong to VH. This theorem says that the norm, or you can say this is dash here, so you can say this is H1 norm, or you can say this H1 norm is bounded by this. Means this is the smallest error. Smallest error for all v belong to this. U is our solution of weak formulation. UH is the finite element solution. So this error is the smallest one, all the errors. Okay. So now if you want to prove this, so writing we have what we have u minus UH. I can write this as u minus v plus v minus UH. What I have done, just add here v and subtract here v and minus this as this for any v belong to VH0. Why we did this? Because you have to prove this for all v belong to VH0. So now here I have choose just one v from this space, and so now I have to prove this. This is less than equal to this. So start from this one. So norm of u minus UH dash total square. I am starting with square. So you can write this as integral over the domain u minus UH dash and dx by definition of the norm. So here I will add and subtract v and using this one u minus v and v minus h. So this can be written as integral u minus UH dash. When you will use this, so here you can say u minus v dash and one more term here. So this will be u minus UH dash, and here will be v minus UH dash and dx. Now you can see this term becomes 0 due to this term becomes 0 due to Galerkin orthogonality. This says that u minus UH dash V dash becomes 0 for all V belong to VH0. Here, this is okay. This is we have here, and this element V belong to VH0, UH also belong to VH0. So their subtraction is also belong to VH0. So this become 0. Okay. So now just we have this one. Here apply the Cauchy-Schwarz inequality. So apply Cauchy-Schwarz inequality here, because this is nothing. This is the norm of inner product of U minus UH. This is what? This is the inner product of U minus UH dash and U minus V dash this. So when you will apply inner product here, so this become norm of U minus UH dash and norm of U minus V dash. So here is one U minus UH dash, so this is cancel out. So this implies norm of U minus UH dash is bounded by norm of U minus V dash, this, which we have to prove here. Okay, so from this theorem we conclude that the this error, you can say H1, this is H1 error, because here is dash derivative is there. H1 error is the smallest one if you will take the difference between U and all element of VH. So this is the smallest one. So one more theorem here in this direction. So what this says, say this is theorem 3, this is theorem 1, this was theorem 2, and this is theorem 3. The finite element solution, UH satisfies norm of U minus UH dash square less than equal to C, some constant summation, n is equal to I equal to 1 to n hi square norm of U dash square over L2. Over L2 of I means at the ith interval. Suppose this is the I interval, this is the I plus interval. This is xi minus 1, this is xi, or this is xi plus 1. So this is over the ith interval. That's why it is summation taken here. Summation all, if you will check this summation, that this can become integral if you will take n goes to infinity. And hi means what? This step length. This is hi. Generally we choose hi is equal to h, uniform step length. But if you are sometime it is not necessary that all the step length in 2D and 3D are equal. So here in 1D just hi is equal to h, you can say, but in not in 2D. 2D it is equal to h is equal to maximum of hi or maximum or hi, this one. So now to prove this, I will take help from the equation number, theorem number 2. So what this says, from theorem 2 we have norm of U minus UH dash is bounded by U minus V dash for all V belong to VH0. Okay, so obviously that this is what? This is finite dimensional subspace and this element from there. So we can choose here V is equal to interpolation of A. We can say this one. Here V is this hold for all, this hold for all V, and V I am saying the interpolation of, or you can say interpolation of U can say this. Here this is the interpolation. Because this is hold for all V, so I can choose anything. So I am saying that choose V is equal to interpolation. This is notation of interpolation. Pi of U. So this is the interpolation of the linear. Obviously that I am here using the linear basis. So linear interpolation of U. So then this become, then star become less than equal to U minus pi of U dash and this. Okay, so now we have a result from the interpolation theory. So I am writing here the result from the interpolation theory, from interpolation theory. What this says, first result is that f is any function. This is its interpolation, linear interpolation obviously. L2 space or some interval I is less than equal to C h square. H is what? The step length. So f double dash over L2 over I. Similarly, there is a second one, f, okay, first derivative. So f minus interpolation of f and its derivative, norm of this over L2I. This is also less than equal to, here this will be h. Here is order is 2, here is order is 1, and f double dash L2. So I will use this result here. F minus its linear interpolation is bounded by CH square and this. So now you have to prove what? You have to prove this is bounded by this one. So start from here, start from the left hand side, and then use this interpolation result. So you will get the result here. So start from here now. U minus UH dash square. This is less than equal to, from the, you can say from here also, squaring both sides. So you will get this. So this is U minus pi of U dash squaring, and you can write this in the integral form if you want integral. So U minus pi of U dash square and dx, or you can write this in the summation form. I is equal to 1 to n over the whole interval, norm of, because this is norm and this is okay. So yeah, either you can say this from here. You can say this is equal to summation I is equal to 1 to n, norm of U minus pi of U dash is a square L2 of, this was L2, but this was over the whole interval, so I am saying the ith interval. Then you will sum, so it will cover the whole domain. Okay, so now apply here this interpolation. This dash is here because this is also dash. U minus its interpolation dash is here. So squaring both sides, so this become less than equal to C. This is C, and the squaring here, so you can say C square, or it is okay. I equal to 1 to n. Hi square, I am saying hi square because I am taking that every interval has some step length, and u double dash, because this is here, u double dash, and square L2 of I. So this we have to prove this. Or you can say, if you define, if you define H is equal to maximum over Hi, then you can write this u minus UH dash square less than equal to some C constant, and so I am taking the square root both sides, so this become H, or this become, if you will sum over the whole domain, so this become u dash L2 over the 2. So you can say that this is H1 norm. H1 norm is bounded by this. So you can say this is what? You can say this is u minus UH. H1 here, if you will remove this dash, less than equal to CH, and u double dash over the L2. So order of H1 norm is 1. Okay. So as you know that when you will apply the computation and you will find the H1 order, so it will be linear order for the linear interpolation. But one thing you can know that, by using the Poincare inequality, this u minus UH is less than equal to this one. So simplify, this is the L2 error. So from this and this you can say that u minus UH is bounded by CH, u double dash, and L. So you can say that L2 error, order of L2 error is also linear, but this is wrong because the L2 order in FEM is 2 for the linear one. So this means this is the suboptimal error estimate. So prove that, because you know that its order will be 2. L2 order in finite element is 2, means this would be H square. But from here, if you will just apply the Poincare inequality, and from here you are going to estimate its order, so you will see that order of L2 error is just linear, which is the order of H1. So that is wrong. So this is the suboptimal error. So if you want to prove this is 2, so I will take some help from some theory. So that is, I will do for the 2-dimensional problem, the L2 order of convergence for the linear interpolation is equal to 2. I will prove for the 2-dimensional problem. This was just all the thing was the 1-dimensional problem. So in 2-dimensional problem, we will prove some theoretical results and also prove that the L2 error has the order of convergence is 2. That is the optimal order of convergence, because in L2 we got 2 order of convergence. So that we will do in the next lecture. So thank you for attending this lecture.